Okay, so today I'm going to talk about low-dimensional manifold regularized neural network. This is basically a plug-and-play neural network regularization technique that focuses on the geometry of both the input data and the output features. So this is joint work with my collaborators at Duke University, well, except for Jiaqi Huang, who's a Duke alumni, and he is now in Baidu Research Lab. Okay, so neural networks and overfitting. Neural networks have achieved great success in machine learning research and applications that we have seen so many great talks throughout this workshop. And when you have large amounts of training data, the capacity of DNN can easily be increased by adding more units or adding more layers to extract more effective features. However, even the big networks with millions of parameters can overfit even like the largest of data sets. What this means is that you can perform very well on the training data, but it doesn't generalize equally well on the test data. Okay, there are a lot of network regularization techniques to alleviate the situation of overfitting. Many of the widely used network regularizers are data independent. For example, you have weight decay, parameter sharing, dropout, DropOut, early stopping, etc. And most of the data dependent regularizations are motivated by the empirical observation that data of interest usually lie typically close to a low-dimensional manifold. For example, you have tangent distance, tangent prop, manifold tangent classifier, and the list goes on. The problem with most of the manifold-based data-dependent regularization is that most of these algorithms only focus on the geometry of the input data and doesn't focus too much on the output features. And some of the algorithms, for example, the first two network regularizers, they need human input of tangent vectors because they want to learn a feature that is invariant with respect to the tangent vector on the data manifold. And these tangent vectors are usually derived a priori based on, say, translation, rotation in the image, or image local scaling. And this is by no means all the tangent vectors that can be manifested by the data themselves. So what I want to convey in this talk is that you can do manifold-based data-dependent regularization technique that focus on the geometry of both the input data and the output features. And you don't have to do it by providing human input of the tangent vectors, and you don't need to locally parametrize the underlying manifold. Okay, so let's take a look at a very simple problem setup. So the MNIST digit classification, so multi-class classification. You have a bunch of input data, which is 28 by 28 images. And so xi, for every xi, it is a vector basically of dimension 28 by 28. So here D1 is 28 squared. And you want to learn a feature. Basically, in deep learning, you want to learn a feature that is a high-level feature of the input. Basically, in Professor Shen's talk, it's just a T. You want to learn a feature parametrized feature extractor f theta, which is a function parametrized by the network weights theta. And now we define a point cloud that is called data feature concatenation point cloud, which is basically just a cascade of the input data and the output feature. This is a point cloud in RD, where D is the sum of D1 and D2. Now we're also assuming there is a manifold, which is an underlying manifold sampled by the data feature concatenation point cloud. All right, now let's explore what's the geometric structure or what's the property of this manifold. Usually, data of interest typically sample or typically lie close to a collection of low-dimensional manifolds. For example, if you look at the digit 1 here, in principle, you only need 2 dimensions to characterize this digit 1, basically the location and the rotation. If you have a more complicated image, you can basically think of it, say, in a wavelet domain. And in a wavelet domain, for natural images, you need to have sparse correspondence or sparse wavelet coefficients. That means you have some correlation within the wavelet coefficients. You cannot just change it willy-nilly. That means the dimension is actually much lower compared to the dimension of the embedding space. So now we have a bunch of points sampling the data point cloud, sampling a collection of manifolds that has a much lower dimension than the embedding space. And in order to find a good feature, or if you want to find a good learning algorithm, you need to find a good feature extractor, basically this f theta here. We want this f theta to be a smooth function on the data manifold. What this says is that if you perturb the input data a little bit, it will not change the feature, the extracted feature will not change dramatically. In Professor Shen's talk, is basically this t has to be Lipschitz continuous in some sense. We are not enforcing t to be like changed dramatically among different classes, but that is actually ongoing work. I'm not going to talk about that today. Also, now we have a feature extractor, which is a smooth function on a low-dimensional data manifold. Then the data feature concatenation manifold should still be a smooth function in a higher dimensional space. So here D is D1 plus D2. D1 is the dimension of the input, D2 is the dimension of the feature, and this manifold M should have a lower dimension than D. Okay, so we know that if F is a smooth function, then the feature extracted by this F and basically the dimension of ML, which is the data feature concatenation manifold, should have a much smoother, much smaller dimension than the embedding space. So that means we can regularize the original loss function by using the dimension of the manifold. Here we are taking the L1 norm of local dimensions because, well, you cannot expect everything to lie on a single manifold with the same dimension. So here, for every P, which is a point on this manifold, we denote MP as the exact manifold on which, to which this P belongs. And this is a L1 norm of a local dimension. Basically, this is basically just the weighted sum of the dimensions. Okay, before we get delving into how to solve this, let's look at some results. This is a very simple test on the MNIST dataset. I just used 3-layer CNN network. and I trained this network on 1,000 training images from MNIST. So the top left figure is basically what you do by directly embedding the original raw test data onto 2-dimension. And the other 3 figures are the feature extracted by the same network using different regularizers. As you can see, if you use these 2 widely used network regularizers, the output features of the test data usually sample basically a 2D region in 2-dimensional, well, in the Euclidean space. That means the dimension of feature is 2. However, if we look at the dimension of the feature extracted by LDMnet, they sample elongated region in R2, and sometimes just sample a point. If you do local PCA here, you will basically say, well, one of the principal value is a lot larger than the other. So what it means is that the feature extracted by LDMnet should sample a low-dimensional manifold. Okay, so the question is, we want to minimize the dimension, but is there any way, or is there any efficient way to calculate the dimension directly? The answer is yes. By using some elegant formula from differential geometry, you can check that if you have a manifold M that is smoothly embedded in RD, then the dimension of M can be calculated using the sum of the coordinate, the sum of the manifold gradient of the coordinate function squared. Here, alpha I is the coordinate function for every point P on this manifold, and alpha I maps the point P into the Pth coordinate. And this is a manifold gradient. We can have a sanity check here. Say if you have a manifold M that is S1, so this is a 1-dimensional manifold in the space R2, then K is equal to 1, and the dimension of the embedding space is 2. We can have a local parametrization, which is cosine theta, sine theta. Then in this case, the metric tensor, which is the inner product between the unit vectors, so it's just a 1. And you can write down the coordinate of the gradient, and they sum up to 1. Okay, so by using that theorem, we know we can replace the L1 norm of the local dimension with the Dirichlet energy of the coordinate functions. And we need this constraint such that at each step, well, we need a constraint that the data feature concatenation point cloud samples the manifold. And the optimization problem is taken with respect to both theta, which is the network parameter, and m, which is the underlying manifold. Okay, so now the problem is, how do we solve this problem? How do we solve this? Well, the most naive idea is basically split with respect to theta and m. So this is the procedure we take. Assume at step k you have some estimate for the network parameter theta and underlying manifold mk. And what you do at step k plus 1 is you first fix the manifold mk and perturb, you solve for theta k, and at the same time you are perturbing the coordinate function. So this time we're assuming that this alpha is not a given function, but some function you want to perturb the point cloud and the manifold. After solving this, you update the manifold by mapping the previous manifold into the new manifold. So at first sight, this might not make sense because alpha should be a fixed function. It's just, if you look at the collection of alpha, it's basically just identity because it's the coordinate function. But if the iteration converges, this actually makes sense. This is basically just a fixed point iteration. Because let's say if the iteration converges, then for large enough k, mk plus 1 will be very close to mk, and this alpha should be very close to identity. And we also have at each step, the point cloud is always mapped into the new point cloud using the function alpha, and the old manifold is mapped into the new manifold using the same alpha. That means at each step, the point cloud always samples the underlying manifold. Okay, so by looking at these two steps, this one is fairly easy to implement. You just need to, this is point evaluation. But for the first step, it's kind of hard to solve because j theta as a network loss function is always non-convex, and you have a nonlinear constraint with respect to nonlinear constraint with respect to alpha and theta because f theta is usually nonlinear with respect to theta. So you have a non-convex optimization problem with nonlinear constraint. And we are doing something ridiculously crazy. We are solving it just using one step of LDMnet. And it turned out that actually this stupid thing actually works. This crazy implementation actually works. So what you do is you split with respect to alpha and theta. When you're solving alpha, you're solving this equation, solving this optimization problem. And theta is basically update, well, this minimization. And you update the do variable. Okay, now let's look at these three updates. The last one is very easy to implement. The second thing can be implemented by solving a stochastic gradient descent with modified backpropagation because we know how to backpropagate j theta. Usually, given a network structure, you know how to backpropagate it. But this term, well, you need to incorporate this term into the gradient. And alpha, the alpha update, which is solving which is solving an energy functional that involves a Dirichlet energy on the manifold. This can be solved using the point integral method, which is devised by Zuo Qiangxi from Tsinghua University. Okay, so let's first look at the theta update. So the extra term is basically just a quadratic term, this EI theta. You can easily take the gradient of this energy with respect to the output feature layer. So basically, in order to backpropagate the gradient, you only need to add this term into the original gradient and propagate it back as usual. So the theta update is very easy. And for the alpha update, by looking at this, you'll see that the alpha update is, well, independent or is decoupled with respect to j. So every alpha j update can be cast into this form. So it's a Dirichlet energy on the manifold plus a quadratic term. And you can take the Euler-Lagrange equation of this minimization problem. So you're basically solving, in order to update this u, you're basically just solving a Poisson equation on a manifold. But the problem is, you're given a manifold, you don't know the dimension of the manifold, and you are just given an unstructured point cloud sampling the manifold. So this can, so we're solving this using the point integral method. The key observation in the point integral method is that you can, after convolving some kernel, well, you can take some heat kernel. After convolving the heat kernel with the manifold Laplacian, this term is approximately equal to a graph Laplacian plus an integral on the boundary. So what this means is that you don't need to discretely, or you don't need to explicitly discretize the manifold Laplacian anymore. You also don't need to discretize the manifold gradient. You only need the point value of this function on this manifold. And this R can be any function that decays exponentially or have compact support. So here is a local Chern-Kirchner error analysis. You can prove that this is OT1/4 estimation. Okay, so now we know in order to solve this Poisson equation, you can first convolve the first equation with a heat kernel. This will give you this term. By using the theorem, you know this term can be replaced by a graph Laplacian, so this is what you have. And now we are making another assumption saying that, well, the point cloud given by the data and the feature concatenation sample the manifold uniformly at random. So basically, I want to estimate this integral using Monte Carlo. So it replace this integral using the sum, and basically solving U is just solving a dislinear system, which can be achieved quite easily. Well, easily for now. I'll explain later. So now this is the full training step. What you're gonna do is you first initialize the network weight, and then you compute the weight matrix among all the data. I'll explain later why this works. Compute the weight among all the data. This is the weight matrix and the graph Laplacian. And then you update alpha, which is solving a linear system. And then you compute the theta k, which is solved by running SGD m epochs. In our experiment, we always set m to be 2. And then you update the do variable and iterate. So compared to traditional or the standard network training, you know that these two steps are the actual steps. Now we want to do some complexity analysis of these two steps. So when you're computing the weight, what we only do is we just construct a sparse weight matrix. So in our experiment, we always truncate the weight matrix to 20 nearest neighbors. And this can be done by building the data into a KD tree and then do an approximate nearest search. And this step can be done with a complexity that converges at worst at O n log n. And after doing that, you have to solve this linear system, because this linear system is symmetric and it's sparse. So you can solve it with preconditioned conjugate gradient. And we also put a cap on the number of iterations, so this step is actually O n. So for now, it's not that big a problem. I will get to that point later. Okay, so I have enough time. Okay, so the experimental setup, we compared our algorithm to most widely used network regularization technique. So this time we are comparing the algorithm to weight decay and dropout. To prove the concept, we are just using a very simple CNN structure. So in this case, we're only taking three convolutional layer neural networks. And let's see the result. As you can see, when the training data is very scarce, when the amounts of training data is very small, the LDMnet significantly outperforms widely used data-independent regularizers. Let's look, you've seen this picture before. The reason why it works so well is that it extracts the features that lie on low-dimensional manifolds, so it's easier to distinguish by any high-level feature extractor, by any softmax layer, basically. Okay, we also have some results on SVUHN and CFA 10 using still a very simple network structure. And again, the result is much better than using very simple weight decay and dropout. To prove that this regularizer is more or less a plug-and-play network regularizer, we also try this on a pre-trained network. So what we did is we basically download a pre-trained network using weight decay and dropout, and then just add a layer, LDM layer, on top of the network and fine-tune it. You can fine-tune it using basically just 2 steps or 2 epochs, and it works pretty well. Okay, so this basically tells you that if you have a trained network, you are not quite satisfied with the result. You can basically give this a try. Okay, another experiment is carried out on the phase matching, the cross-modality phase matching, what you do is the objective of this experiment is to match the near-infrared image to the visible light image. For example, when you're given this image, you want to find the subject in the visible light domain. There are a lot of works on face recognition using just the visible light images. And the reason why it works so well is that you have a huge amount of face recognition images in the visible light domain. But you don't really have that many images in the near-infrared domain. Yeah, this is the drawback. Because you don't have that many images in the near-infrared domain, it's hard to train a neural network using just a limited amount of near-infrared image. And also, the near-infrared and the visible light phase matching is a cross-modality matching, which can be quite problematic. So the author in this paper, well, two of whom are actually the collaborator of this in our paper, introduced a way to transfer the breakthrough invisible light image into the near-infrared domain. What they did is they basically can use any pre-trained network as a feature extractor. And then this network can be treated as a black box, and then they do two steps to basically modify both the input and the output of the near-infrared image. What they did is modify the input by hallucinating visible light images. What they did is extract matching patches and then hallucinate a visible light image by using a patch-based CNN. So you can hallucinate a visible light image using near-infrared image, and the visible light image is input into the CNN, and then the next step is to learn an embedding algorithm, embedding of the DNN feature at the output. So basically, that's what they have done. They modify these two steps. So in our work, we are focusing on the second step. So we use the pre-trained CNN on the pre-trained DNN on visible light domain as a black box, and we only need to train a shallow embedding network. Okay, so using a fairly simple structure, just two layers of fully connected layer, and let's see the result. If you're using VGG phase directly, which is trained on the visible light image and hasn't seen any data from the phase matching data set, the accuracy is 74. If you're doing some embedding in the output layer, the accuracy actually increases a lot. Well, significantly in some sense. However, the most important thing is by looking at the last three results. These three results are obtained by using the same network structure, but with different regularizers. If you're using weight decay and dropout, you can see actually the accuracy deteriorate compared to VGG phase. What it means is that by giving this limited amount of training data, in this case it's actually just 6,000 images, you can overfit like crazy. It performs very well on the training data, but it doesn't generate as well onto the test data. But if you're using manifold-based LDMnet, you can actually significantly outperform the original pre-trained CNN. And this is very easy to do because you only need to train a shallow embedding network, which is crazy stupid, and very, very speedy. Okay, you can also visualize the results in R2. So if you have a VGG phase, in this visualization, every subject is distinguished by different colors. And for every subject, the filled circle is the images of the visible light images, and the unfilled diamond will be the near-infrared image. As you can see, if you use the vanilla VGG phase network, these two, the same modality image of the same subject do form a same cluster. But if you look at two different modalities of the same subject, they actually form two different clusters. And if you're using weight decay or dropout as embedding network, regularize the embedding network, you can see it actually deteriorates because you're separating them even further. But if you're using LDMnet, it can somehow, in some sense, push the features of different modalities into the same low-dimensional manifold. So the clusters are pushed towards each other much closer. Okay, I guess I'm fast. So the conclusion is LDMnet is a general network regularization technique that focuses on the geometry of both the input data and output feature. And it directly minimizes the dimension without any explicitly parametrization, and it significantly outperforms any widely used network regularizers. So here, now let's go back to the limits. So if you recall, well, there is no politician in the room, so I believe you recall. In our setup, you need to compute the weight matrix. And it's kind of hard if you have a lot of data. That's especially true when you want to do like say 2,000-fold data augmentation, because in that case, you basically you have to compute the weight matrix that many times. And in that case, this log n complexity might actually pick up. So what you can do is quite simple. You can, in our work, you are modifying the manifold at each step after m epochs of training. What you can do is basically just for every batch of data, you can perturb the manifold within that batch of data. In that case, it's just ON. So that is something that can be done later. And there was some also open question of this work. For example, what's the convergence analysis of that crazy splitting algorithm? And also, something we're doing right now is to analyze the complexity of LDMnet. Basically, we want to have a bound of the Rademacher complexity that can basically provide a bound on the generalization error. Okay. Well, I guess no one's going to complain about me being fast, considering this is the last talk. So, any question?